I will keep giving you some important concepts that you need to understand the material. All right, so that's where we were. The last item we were discussing was the concept of equilibrium. And I said then that a simple way to describe what equilibrium is in thermodynamics is essentially to say that nothing is happening in the system. That's a very plain way to express it. But if you want to be a little bit more formal, then you say what is written there. It's a condition of balance characterized by the absence of driving potentials. And at the very end of the lecture, we were talking about driving potentials. And what's a driving potential? Can you give me an example of a driving potential? You can even give me the one from the end of the lecture. Somebody else? How about you?
I have no idea.
You have no idea. Were you here?
Yeah.
Okay. What about you? Anybody, raise your hand if you have an example of a driving potential. A temperature difference, right? You have another one? The same one. Yes?
Catalyst?
Well, you're making it a little bit. Maybe a variation in distribution of a catalyst. But at this point, really, it's a variation in something. So a variation in temperature will produce heat transfer. Right? So temperature in one part of the system is higher than another part of the system, then heat transfer will occur. Can you think of another one? Another difference that would make something happen? Pressure difference. What happens if I have a pressure difference within a system? What will be moving? Fluid, or part of the substance that is in the system. Say if it's liquid or a gas, you have a pressure difference within the system, then a flow will occur. And just like that, you can think of many others. But for the time being, so equilibrium would be that would mean that yes, sir. Does he pay you? He's so far back there. Yes? I'm sorry? This microphone is not for you guys. This microphone is for the video over there. So that's why you guys need to be quiet, because I don't want to have to carry another microphone if I don't have to. So that's why I checked last time. Make sure you hear me in the back. If you don't, then raise your hand and I'll try to speak a little louder. Or you're welcome to move down. You want to come down? Speaking to you. Yeah. There's plenty of seats. There is one here, front row. So, so that's what equilibrium is. So typically you would have no temperature difference within the system, no pressure difference within the system. In fact, if you pick any property of that system, then you would find that that property is the same everywhere within that system, and that would define a condition of equilibrium. Now, the next concept is the concept of a process in thermodynamics. What is a process? And it says there is a transition from one state to another state. We already defined state last time. So you know what a state is. In fact, it's a few lines above that. The state was a certain condition that the system is in and is characterized by whatever properties it has. So if I go from one state to another state, then that variation in the state of the system occurs by means of a process. So I have a process takes the system from one state to another state. So I could, write that in a simple schematic. I have the system here in state 1 on the left. Something happens to that system, and then it goes to state 2. And that is a process. And of course, what we call the process path is really a succession of states as you go from the original state to from the initial state to the final state. So you have certain initial state, certain final state. As you go from the initial to the final state, you go through a series, an infinite series of many other states that are all intermediate states. So typically we would do this by plotting two or more properties. So one way you could think of this is if I take I pick two properties. For example, I could say let's plot, for example, pressure versus volume, right? Two properties of a system, and then initially say that we are at this volume, so I call it V1, and this pressure P1 that define our initial state, and then a process takes place and it takes me on a certain path to the final state. So here is V2 and here is P2, and let's say that I am going that way from 1 to 2. So that's my process. But what I am saying is that all along that process path, I have infinitely many intermediate states. Right? So I can stop anywhere, and that would, of course, be a different intermediate state. So in terms of the definition of equilibrium, what needs to happen for a process to take place? Or what is the connection between that process taking place and equilibrium? Can you connect the concept of equilibrium to the concept of a process?
A new process has to reach a new equilibrium?
No, not exactly.
For the process to be in equilibrium from going point 1 to point 2, you can't add any energy.
No. I mean, can a process take place if I'm in equilibrium? No. So the connection is actually then a disconnection, because for a process to take place, you have to be away from equilibrium. If you're in equilibrium, remember I said nothing happens. So if a process takes place, that means that the system is not in equilibrium, because otherwise nothing would happen. So in general, in a typical engineering system, something has to happen, otherwise there is nothing to study. So suppose you're looking at the internal combustion engine, you're trying to find out what's happening inside the cylinder with the air and the fuel that came in. Obviously, for things to be happening, you must not have equilibrium. Isn't it much better up here in the front? Yeah. So we need to be away from equilibrium for a process to take place. And that actually makes things very complicated. So we come up with another concept to help us out. And that concept is this one. A quasi-equilibrium. So a process takes place. It cannot take place in equilibrium because that's contradictory. But we can say that a process takes place in quasi-equilibrium. And what do you think that is? What's quasi-equilibrium?
One thing the same when you change the other.
Nope.
Process goes by very slow.
No, it's not an equilibrium. Let me ask you right there. You just blew a nice chewing gum bubble. What is quasi-equilibrium? Some sort of fake equilibrium. Okay? There is a better word than fake for quasi. Anybody knows what quasi means? A synonym for quasi? Nobody? Yes?
Semi-equilibrium?
Yeah. What about almost? Right? So quasi-equilibrium is really almost equilibrium. So when we say that a process takes place in equilibrium, in quasi-equilibrium, what we are meaning is that it takes place in quasi-equilibrium. What do you think has to happen for a process to take place in quasi-equilibrium? Who said that?
A slow process.
It has to be very slow. And those two concepts are really parallel. So a quasi-equilibrium process has to be a very slow process. Because the idea is that you only allow the system to deviate from equilibrium a little bit. So you make a little variation, a small variation occurs, then the system goes to the next step. So if you go back to this plot, say you started here, then you allow for a small variation to take place, and then the system maybe moves there. And so it's like it's almost in equilibrium. It's just a small departure from equilibrium every time. And it keeps going until it makes it to the final state. The problem, of course, is that in reality, if you were to do that, it would take forever. However, it's still a very convenient tool for us to study processes, at least at the very beginning, to consider them to take place in quasi-equilibrium. And we will do that very often. Make the assumption that things are occurring in quasi-equilibrium. All right. So if, for example, and here's a more formal definition, a process in which each intermediate state is only infinitesimally removed from equilibrium. It's sort of putting together all the ideas that I just gave you in some nice text. A process in which each intermediate state is only infinitesimally removed from equilibrium. So let's say that we look at a very simple system like this that we have been looking at. I have a gas in a cylinder. It is fitted with a piston, and suppose that I'm interested in compressing this gas, so I want to push that piston down by applying a force. If I do it very fast, as I would do it normally, then I would be significantly away from equilibrium. Because imagine that I start pushing that piston down, what happens initially? Let's say that that's air in that cylinder. So when I start pushing, what part of the air gets compressed? Near the very top. So you might expect that there might be a compression near the top, but not really near the bottom, because it'll take a while for that information to travel down. So you'll have a deviation from equilibrium. There'll be maybe a higher density, a higher pressure near the top. Maybe that's going to drive some of the gas even down, because as we said, if there is a pressure difference, the gas might move. So we'll be away from equilibrium. But I don't want that. I want this to happen in quasi-equilibrium. So one way I could do it would be, for example, by adding infinitesimal weights rather than try to push the piston down with a finite force. So I think about it, instead of putting a large weight on top of the piston to push it down, you're just going to add infinitesimal amounts. So you put a little piece of weight, the piston goes down an infinitesimal amount, and then you keep doing that, you keep adding. Eventually you accomplish the same thing. The volume will go down, pressure will go up perhaps, but it will happen in a very gradual manner. And that's what we mean when we talk about a quasi-equilibrium process. Any questions? All right. Now we talked about properties. Let me flash this back again. At the very top, thermodynamic properties. Now, remember, we agreed that a property is a characteristic that helps me describe the state of a system. So we talked, yes?
So for the quasi-equilibrium process, we would use that more for collecting data, right? Not for
We'll do it for calculations, actually. Yeah, when we do our calculations in Introduction to Thermodynamics, we'll most of the time, if not all of the time, assume that processes are taking place in quasi-equilibrium. We will learn a little bit about the departure from that approach near the end, when we go to the second law of thermodynamics. But at least for the first part of the course, the first few weeks, we're really going to assume when we're doing our calculations that the processes are taking place in quasi-equilibrium. All right? So let's talk a little bit more about properties. And let's classify them. So we have properties. Let's talk about types of properties. One way we can classify properties is by calling some of them extensive and some of them intensive. And the difference between the two is actually very simple. Extensive properties vary directly with the mass of the system, whereas intensive properties are independent of the mass. Another way to look at this is an extensive property will depend on how much mass you are taking into account when you are evaluating that property. Whereas an intensive property, you don't. It doesn't matter what sample you use or the size of the sample of that system, that property will be the same, with the assumption that the system is in equilibrium. So with that in mind, can you think of an extensive property? A very simple one that depends. Hold on, let me ask other people. I don't want to give you all the floor. I'm happy that you're participating a lot, but yes?
Inertia.
Huh?
Inertia.
And how do you define inertia?
Usually it's the mass times the radius squared.
Well, mass times something. Okay. I want something even simpler than that. It's part of what you said, though. Yes?
Density?
No, I want a simpler one. Who said that? Yeah, mass itself. Mass itself is the most obvious extensive property, because I told you, this property, the value of this property will depend on the amount of mass that you're using to sample. So obviously the first one is mass. Mass itself as a property will depend on how much mass I use to sample that property. So here's a few. What about an intensive one? Give me an example of an intensive property.
Temperature?
Temperature. Somebody said pressure back there. Those are intensive. Always think of when you're trying to answer the question about whether something is extensive or intensive, you can always go back to looking at a system like that, where the process is taking place in equilibrium. So if I look at this gas down here, it doesn't really matter what sample I use to measure the temperature. I could use some gas from near the piston, some gas near the bottom. As long as it is in equilibrium, that temperature is the same everywhere, and the temperature will be independent of how much mass. Or if I take a small sample or a larger sample, it will be the same temperature. Same for the pressure, and the opposite, of course, for mass or any other extensive properties. Another extensive one, volume, right? Okay, so let's come back to this one. Density. Extensive or intensive?
Mass per unit volume, so mass.
So what do you think?
Extensive?
Huh?
Extensive?
Well, suppose I go back to this, and I said this system is in equilibrium, this gas, sample the density. Will you get different values depending on how much gas you sample? You'll get the same. So in that sense, it's really intensive. And what is making it intensive is that you're dividing by the volume. Right? So it's mass, but it's divided by the volume. And that's going to be, if the system is in equilibrium, it's going to be proportional. So you'll have the same density no matter how big of a sample you take, because the system is in equilibrium. But here's a few more. So mass, volume, energy will depend on the amount of mass. Temperature and pressure, you gave me those. I added two others on the right-hand side, and you can see that they are the same one on the left. I have volume and energy, but here I have specific energy and specific volume. Does anybody know what those are? What is specific volume?
You divide by the volume of water.
No. Good try though.
Just the inverse of density.
It is the inverse of density, which means that what am I doing with the volume?
Amount of energy it costs to burn one.
Making it too complicated. What am I doing with the volume to get specific volume? Divided by the mass, right? Is the inverse of the density, he said, which is correct. So density is mass over volume. Specific volume is volume over density. I'm sorry, volume over mass. So by dividing it by the mass, it becomes specific in what we call specific in thermodynamics. So specific energy is then energy divided by what? Mass, again. So it's precisely the same idea as we're doing with the density. By dividing by something that is proportional to the mass, in this case the mass, we make it intensive. So we will use a lot of specific properties as we go along. You start doing calculations, you'll find out that when you're using data, you'll typically use specific properties, specific volume, specific energy, specific enthalpy when we talk about enthalpy and so on. They are just the same extensive properties but divided by the mass. You had your hand up.
So if you were to divide any extensive property by the mass, you can get a intensive property.
If you take typically if you take an extensive property and divide it by the mass, you get an intensive property. So you can do it with any of those. Wouldn't make sense, of course, to divide temperature by the mass. You could do it, but it doesn't really help us in any way. So there it is. Specific means per unit mass. How do we tell them apart? How do we know if a property is extensive or intensive? By the case in which we write it. So that's why I say here, use lowercase. So if I write capital E for energy, then lowercase e would be specific energy. If I write capital V for volume, like I was doing in this plot a little while ago. So if this is the actual volume, capital V sub 1 and capital V sub 2, then if I want the specific volume, I will write it as a lowercase. So lowercase denotes a specific property, capital denotes an extensive property. So for example, specific volume, which we were just talking about a moment ago, take the volume divided by the mass. The units in SI units is, of course, cubic meters per kilogram. Or, as I said, energy. Specific energy, lowercase e, would be capital E, or total energy, divided by mass. So joules per kilogram, if I'm using SI units. All right. Okay, let's see. So we talked about processes. So for example, I put an arbitrary process in this plot, but I could have, for example, thought of another process. So let's leave that one there, but put another one somewhere here. Doesn't matter that these lines will cross, where I maybe start here and I go straight up to there. What is particular about this process with the black dashed line? It occurs at constant volume. So processes like that are important to us. I could also do another one where I just do it like this. Okay, so I go from 1 to 2 along a horizontal line, and now this process is taking place at constant pressure. So we will often encounter processes like that, so we give them names. So there's 3 of them right there. Some types of processes. An isothermal process takes place at constant temperature. An isobaric process takes place at constant pressure. and an isochoric or isometric process takes place at constant volume. So I used in my graph here, I gave you examples of a isobaric, the blue one, and isometric, the black one. So unless I give you a little bit more information, I could not put an isothermal process here because this is pressure versus volume, so it's not clear where the temperature is. But it will be clear later. So there is another type of process that will be very important for us. And I already told you a little bit about them, about these processes in the first lecture. When we look, for example, at the power plant or the internal combustion engine, does anybody remember what type of processes were occurring there? There was something particular about those processes.
Cycle.
He's got it. A cycle, right? So that's an important. So how do I define a cycle or a cyclic process? With your own words. Turns back to the beginning. So in a cycle, the system returns to the initial state. So if the red dot there denotes the initial state, then of course I go around in one or more processes. I can divide a process into sub-processes, so I can do that. But as long as I come back to where I started from, then that's a cycle. It's a cyclic process. We saw a very complicated one when we looked at this, right? The indicator diagram for an internal combustion engine. I said, well, if we start at R, we go on a series of processes from R to A, C prime C, Z, B, back to R. So going from R to R defines a cycle. Okay, let's see, what else? I'm sure you all know these things, but I'll flash it here just to make sure. I will only give you problems in SI units. So most of the, maybe once in a while I might give you a problem where you have to use English units. So most of the problems you're going to have to deal with SI units. It's a lot easier to convert back and forth because it's all decimal. So make sure you remember all those things. All the units for the important quantities and all the conversions and so on. Little review about units. We already talked about density, but let's flash it here again. Density, mass over volume, or the inverse of specific volume. So you have it right there. 1 over lowercase v. Remember, lowercase v was volume over mass. So the units of density in SI, kilograms over cubic meter. What about pressure? This is a more or less formal definition of pressure. All right? What am I doing there? When I say the limit when dA goes to 0 of dFn over dA. That's how you define pressure, really. So it's a force normal to a surface. Take a force normal to a surface. Divide the force by the area, but take it to the limit. As the area gets smaller, that defines pressure at a point. Okay? Units of pressure, newtons over meter square. Okay? And what is that? What is a newton over meter square? It's a Pascal, right? So a Pascal, newton over meter square. What about 1 atmosphere? How many pascals? Yeah, 101 kilopascals, or 0.101 megapascals, or 14.7 pounds per square inch. And the other one that you'll see a lot is the bar. 1 bar, 10 to the 5 pascals, or 100 kilopascals. Just you're going to be doing a lot of calculations with pressure and so on. So just to make sure that that you have that. Okay, now let's talk a little bit about the difference between absolute pressure and gauge pressure. What is the difference? What is gauge pressure?
The difference in pressure between like a sealed container and the atmosphere.
Right. It's usually the pressure referred to the atmosphere. So when you take the tire pressure, right, in your car, what is that? Absolute? That number that you get, 32 psi or so, is that absolute or gauge?
Gauge.
That's gauge, because that's measuring against the atmosphere. So this diagram is useful to see the difference. It's not that complicated. So this is just pressure. The horizontal is nothing. We just care about pressure measurement. So we're going from 0 to some value. This is absolute 0 at the bottom. So that would be, of course, vacuum. Absolute vacuum. Nothing. 0 pressure. And then the other important entries here at atmospheric pressure is right there. PATM. So that's whatever units you're using to denote atmospheric pressure, it will be there. And so here is a system, for example, that is at this absolute pressure 1. And here is another system that is at absolute pressure 2. So those would be the absolute values read from 0. The gauge pressure, of course, would just be the difference between the absolute value of the pressure and the atmospheric value. So this is ordinary pressure, ordinary gauge pressure, this delta P from atmosphere to the absolute 1. And this one, because it's below atmospheric pressure, we call it a vacuum pressure. So vacuum pressure would be a pressure that is under atmospheric value. But real vacuum would only be if you have 0 pressure. All right? Any questions? Okay. Couple of things, couple of other things that I want to review with you, and this is all review, as you can probably tell. Whoops, let's make that a little smaller. So this is a simple calculation, of course, of the pressure at the bottom of this tank. So I have a tank that has a certain area, cross-sectional area. I have, for example, a liquid to a certain depth, capital H. The volume in the tank is, of course, area times the depth. How much does that water weigh is, of course, density times gravity times volume. So if I want to come up with the pressure at the bottom, of course, is the weight of the water. The weight of the water divided by the area. So rho GH. It's a handy expression to determine the pressure at a certain depth. And this is really fluid statics, which you have probably seen before and that you will see more of in fluids. But this is a handy expression that everybody should know, right? The pressure at a certain depth is just rho G times the depth. And you can use that principle in a simple manometer. You know, if you're using a very simple manometer to find the pressure, for example, in this tank. So here I have a tank that has a gas, and this gas is at some pressure PT, and I want to determine what that pressure is by using this very simple manometer. So I use that principle that I described above, that the pressure at a certain depth is just rho GH. I can use that here to arrive at this expression. And this is fairly simple. Let me go through it very quickly. First of all, we agree that the pressure at A is equal to the pressure at B. So that statement is right there. These two pressures are the same because they are the same depth. These 2 points, A and B. Now, I also say that the pressure in the tank is equal to the pressure at A. How accurate is that? How good or how bad is that? What is the error that I am making if I say that the pressure in the tank is the same as the pressure at A, which is the interface between the gas and the liquid. How good or how bad is that? Nobody?
If it's in equilibrium, shouldn't they be equal?
That's a very good point. That's a very good point. If this is in equilibrium, it should be equal, right? Now, think about the following. This is in mechanical equilibrium, but there is something external that is affecting this system, which is gravity, right? So what gravity is doing for us is, of course, this is not moving, because if I just set that there and I don't disturb it, it will not move. So it is in equilibrium, it's mechanical equilibrium. But gravity, which is an external agent, is making some other things change, right? So if I think of the pressure, right? If I think of the pressure, in fact, if I go back to the first diagram, if I think about the pressure here, we're actually saying that the pressure is not the same everywhere. But that's all because of gravity. That's what is throwing off the equilibrium, because we have a pressure difference between the top and the bottom. Say that here at the top, this is open to the atmosphere, so I have atmospheric pressure above. But we just said that the pressure at the bottom is this value. This is a gauge value, rho gh. So there is a pressure difference, but it's due to the gravity. So you got to keep that in mind when you're looking at this, that there is gravity that is disturbing the pressure. So it's not in equilibrium because it is in mechanical equilibrium, but the pressure is not the same. But the error that I am making here, if I take gravity into account, is what? What would be the difference in pressure between here and there? It would only be whatever weight this column has on top of A. But that will be negligible, because this is a gas, and the density of the gas will be a lot smaller than the density of the liquid that I drew in red. So that's the error that you would be making. The error of the weight of a very small column of gas. That error, I mean, that pressure is not always negligible, right? Give me a simple example where the pressure at the bottom of a certain column of gas is not negligible. Atmosphere. Right? Pressure here is due to the weight of the atmosphere above us. Right? That's, of course, a very large depth. In that case, it's not negligible. But in a simple experiment in a lab, for example, that's irrelevant. That's why I'm saying that pressure at A is the same as pressure in the tank. That's the statement right here. And of course, the pressure at B, I can determine from the column of the red liquid that is sitting above B. So that's this depth H, capital H, from the interface here with the atmosphere and B. So the pressure at B is atmospheric pressure plus rho gh. And I put the rho in red because it's the density of the liquid, of the red liquid. So in the end, I come up with an expression that tells me the pressure in the tank is atmospheric pressure plus this, the weight of this column, right? That is denoted by H. That's a simple, very simple manometer. Okay, so with this in mind, let me do it here. We can look at an example. So let's look at this one, which actually is one of your, this is one of your homework problems. This problem has two parts. I'm just going to tell you a little bit about the first part, and then the TA probably will go over some of the second part. So this is Chapter 1, Problem 80. It has this arrangement. There are two tanks. They're both open to the atmosphere, but they are connected by a line. There's a pipe connecting the tanks. And there is a valve that is in that line, but that valve is closed. So with this valve closed, the first part of the problem is simply asking you to determine the pressure on both sides of the valve. What is the pressure on the left side of the valve? What is the pressure on the right side of the valve? That is easy because it's a straight application of what we were just doing. So what is the pressure? So this one I'm calling A, the one on the right, and B, the one on the left. You can see that I have denoted this height of the liquid in the right tank, in the A tank, as H sub A. And here on the left side, I actually divided it up into a lowercase h, which is from the valve to the bottom of the tank labeled B. And then there is an H sub B, which is the actual depth of the liquid in the tank labeled B. So finding the pressure at the bottom is, of course, very easy. This is what we know. So we know how much mass there is in each tank. We know M sub A, M sub B. We know the area of each tank, capital A sub A, capital A sub B. We know the heights, and we know the density. So that with all that, the problem is very simple. So to find the pressure on either side of the valve, you can, of course, express these H's, H sub A and H sub B, as the ratio of volume over area. And then if you bring in the mass for the volume, then you can find an expression for A sub A and H sub B. That's very straightforward. And then on the A side, then of course the pressure at the bottom, which is the pressure that we're looking at, that would be the pressure on the right side of the valve, P sub A, is atmospheric pressure plus this column, which is rho g H sub A. That's easy. And then the pressure on the left side of the valve is, of course, atmospheric pressure plus the total height, which is now H sub B plus H times rho g. So that's easy. That part of the problem is easy. What you have to think about, and I'll let the TA talk a little bit about it on Friday, tomorrow, is what happens if I now open the valve. So if I open the valve, now, of course, if I open the valve, the system will be away from equilibrium. Right? So, because the fluid will try to flow to balance the pressures again. And in the end, I have to have the same pressure across the valve, because I will reach a new condition of equilibrium. So, once I reach that new condition of equilibrium, the question is, what is going to be that pressure? And of course, the problem has to do with determining what the heights will be in the tanks when everything is done. But I'll let you think about that, and if you go to discussion, you can see a little bit more. Any questions about this? Okay. Let's talk about something else. Actually, let me do this first. Actually, let me do this right now. Here is a problem that you will see once in a while. The same cylinder that we have been looking at. So I have a cylinder, there is a piston on top, but to make the problem more complicated, we add a spring. So there is a spring there at the top of the piston that can be compressed if the piston moves up, or stretched if the piston moves down. Now, in this particular case, you can see that I have chosen, and this was my choice, to set the equilibrium position for the piston, for the spring, to be when the piston is at the very bottom. I allow, therefore, the thickness of the piston, so when the piston is sitting at the bottom, that spring is in equilibrium. So it's neither stretched or compressed. Now, as the piston moves up, because there is presumably a fluid in here, or a gas or something, if the volume inside increases, then the spring gets compressed. But I make it a linear spring, so I say this spring has a constant K, which is a linear constant, meaning that the force is going to be proportional to the amount of compression or extension of that spring. So that's simple. So how do I determine, for example, what I really want to get in a problem like this, I want to get a relationship between pressure and volume. Let me go back to that, to this plot. Precisely in this example, I use pressure and volume to describe certain processes. So it is very important for us to be able in many problems to obtain a relationship between the pressure and the volume in a system. And we can do that in this problem. How do we do this? By simply doing a force balance on that piston and assume that it is in equilibrium. So if this piston, which by the way has a certain mass m, if this piston is in equilibrium, what should happen? Sum of the forces is zero. So that's all you need to do. So if I do the forces, which forces do I have acting there?
Gravity, force of spring, and then the force given off by the gas in return.
Okay, so pretty much weight due to gravity, the spring, you said, and the gas, or I should say perhaps the gases, right? Because there's gas on both sides. Right? This is open here, presumably to the atmosphere, so there is also a pressure there. So you have 4 things to worry about. So all you have to do is you do that force balance, and that's a very simple force balance. Right? PA is the force due to the gas inside the cylinder, and I made that positive, so I'm making forces pointing up positive. So PA is positive, is in the upward direction, but then I have minus P naught A, which is due to the pressure outside. It's negative, is pointing down. The weight is negative, is pointing down, minus mg, and the force that the spring is producing on the piston, which is, as we said, linear, and is minus kx. So those have to be 0. The piston is in equilibrium. Does that mean it's not moving? It could be moving. How? A constant velocity. Right? So the piston could be moving at constant velocity. So that's important for us because if there is a process taking place, you know, we want the piston to move. But it will still be in equilibrium if we make the assumption that it's in equilibrium and it's moving at some constant velocity. And it doesn't matter how fast or how slow. We want to make it very slow. We want to make it in quasi-equilibrium. So we say it's moving very slowly with some constant velocity. So you got all of that in there. The volume, of course, inside the cylinder is the area times the displacement. And the only reason I'm putting that down there is because I want to get rid of that x. Because I'm typically not measuring x. I'm going to be measuring volume. But I can make that substitution and I end up with this. If I solve for the pressure inside the cylinder, I find that the pressure inside the cylinder is P naught plus mg over A plus kV over A squared. Okay? And now I have obtained a relationship between the pressure and the volume in the cylinder. What type of a relationship is that in this problem? What type of a relationship is here between pressure and volume? Huh? Inverse? Where is the inverse? Linear, right? It's a linear between pressure and volume, right? It's linear. Would you agree with me that I can write that whole expression like this? Right? P naught is a constant, atmospheric pressure. The mass of the piston is constant, gravity is constant, the area is constant. So the first 2 terms of that equation are constant. I'm just calling them C1. And of course, K over A squared is another constant. I'm calling it C2. So that's just to show that in this problem, as represented by that drawing, there is a linear relationship. So if I now go back to my plot here, and I want to draw that process in this plot, what do I draw? A straight line. Right? I would need to draw a straight line. This is getting a little cluttered, but let's pick, for example, the same 2 points. So I'm just going to go and put a straight line right there. Right? That would be the process that takes place in this cylinder. It would look like this in a PV diagram because it's a straight line. All right? You will see problems involving this geometry once in a while. Does anybody have any questions? Okay, so what if I don't have the spring? What changes? Take the spring away. What is the relationship between pressure and volume? Same? I'm taking the spring away. Take the spring away and get a new equation and put it on this diagram. Which one? It would be isobaric. Right? If I take the spring away, I'm taking the C2 away, so pressure is constant. Right? C2 becomes 0, pressure is constant, so without the spring, the process would be the one denoted by the horizontal blue line, right? Without the spring. Okay. Let's talk a little bit about temperature. So enough about pressure for now. Let's talk about temperature. How many temperature scales are you familiar with? 1. How many?
4.
Yeah, that's fair enough. 4. Centigrade, Fahrenheit, Kelvin, and Rankine. Right? Again, because we're going to be working mostly on with SI units, really centigrades and Kelvin will be important. There are some problems in which you must work with absolute temperatures, and we'll see those later. There are some other problems in which it doesn't matter. Typically, if all you need is a temperature difference, then it doesn't matter. But if you need an absolute temperature, then you have to work with Kelvin. So, of course, Kelvin and Rankine are absolute scales. They start from absolute 0. You already know that. And then you have your conversions from Kelvin, for example, to centigrades to Kelvin, Fahrenheit to Rankine. Those you have somewhere in your database. And of course, centigrades to Fahrenheit and Kelvin to Rankine, in case you need to do that conversion. So I'm sure you're familiar with those. So on Tuesday, I told you that this course essentially deals with 2 laws, which were first law of thermodynamics and second law of thermodynamics. However, there is something that is called the 0th law of thermodynamics. So let's quickly talk about it. Does anybody know what the 0th law is? You do?
If A equals B and B equals C, then A equals C.
Yeah, it's a very trivial law. But it has to do, your A, your B, and your C are temperatures. That's all. But that's exactly what you said. That if I have 3 systems, A, B, and C, and I know that the temperature of system A is equal to the temperature of system C, and the temperature of system B is equal to the temperature of system C, then the conclusion that I reach right away is that even though I didn't make a direct measurement of, or a direct comparison between A and B, that the temperatures of A and B must be the same. So if the temperature of A is equal to the temperature of C and the temperature of B is equal to the temperature of C, then TA equals TB. That simple statement that is obvious to us is called the 0th law. Right? Okay. We talked about energy on Tuesday. And in particular, I talked about internal energy. Remember, I told you when we talk about energy, there are many forms of energy. You know about kinetic energy, you know about potential energy, chemical energy. In thermodynamics, we try to make our life simple by defining something that we call internal energy. And I mentioned it to you on Tuesday. What is internal energy? What is internal energy associated with? Molecules. Right? So the microscopic nature of our system. The microscopic nature of our system says that there are molecules in there. Those molecules have energy. And usually you can talk about those energies. There is potential energy associated with the distances, say, between molecules. There is kinetic energy associated with velocities of those molecules or atoms in those molecules. And of course, there are vibrational energies associated with molecular structure. Remember, we're looking at thermodynamics from what we call a macroscopic approach. So we don't deal with the molecules. But we have the information about what that energy is. Because people make measurements, determinations about difference in energy of systems in different states. And all of that energy that is associated with all that molecular activity, we call it internal energy. That will be by far the most important form of energy that we will have in our systems. I told you on Tuesday that on occasion we will add kinetic energy, which is macroscopic kinetic energy because of macroscopic motion, or that we could add potential energy with respect to a gravitational system. But for the most part, it is internal energy that we're going to be dealing with. So we use capital E for total energy. All of the energy modes together make up capital E. The internal energy we call capital U. So just internal energy is capital U. That is, of course, an extensive property, because the amount of energy contained in a system will depend on the size of that system. And then, of course, what we do is we usually work in terms of specific internal energy, which is now lowercase u, and that is, as we have seen earlier today, the extensive internal energy divided by the mass. Units, of course, for energy are joules, for mass are kilogram. Joule turns out to be a little bit too small of a unit for most problems, so we typically express internal energies in kilojoules per kilogram. And you will work with those units. Okay, let me see if there are any questions. I'm going to switch gears a little bit. This is more or less the end of the introductory review. And what we're going to do next is the following. Let's see how much time I got here. I've got enough time. We're going to do an experiment. And not surprisingly, we're going to be looking at a system like the ones we have been looking at. The typical thermodynamic system. Cylinder, piston, and a substance in here. In this case, as you can see, that substance is liquid water. So I'm going to have liquid water in a cylinder, fitted with a piston, exposed to some pressure outside. Let's say that I can control this pressure out here to be whatever I want it to be. And for simplicity, let's ignore the weight of the piston. So let's say that the weight of the piston is insignificant compared to that pressure that is outside. If I say those things, then what is the pressure in the liquid water? Huh? What is it? What is the pressure in the liquid water? Well, and using my notation? P naught. All right? So the pressure is P naught. Remember, I'm neglecting the pressure, the weight of the piston. You can just go back to the previous derivation and see what happens. No spring, no mass for the piston. It's just P naught. And the experiment that we're going to conduct is very simple. I am going to add heat to this liquid. And I want to do it very slowly. So this process is going to be a quasi-equilibrium process. So I have the liquid in there. I'm going to start adding heat to it. And I'm going to make a plot. And the plot that I want to make as I do the experiment is a plot of two properties. So I'll do, we were doing pressure a while ago, but now let's do temperature. So I'll put temperature here on the vertical axis, and I'll put volume here, extensive volume. Right? And I'll start somewhere. So let's say that liquid water, if I go back to my, I could measure the temperature, measure the volume, and then put it on this diagram. So let's say that that's there. Let's call that V1, T1. All right? And I'm going to start adding heat. So add heat slowly. What happens? A process takes place. What direction will that process go on this plot? You can see how easy it would have been if I had put pressure versus volume. Because if I had put pressure versus volume, what direction do we go? Pressure versus volume. What direction would we go? Huh? Not in this plot, but in the pressure versus volume that we were looking at a while ago. On this plot. Where would I go?
Wouldn't it expand?
Huh?
Temperature?
I'm sorry?
Wouldn't the volume expand with temperature?
Go down.
The volume will expand if I start heating this thing up. That piston, they didn't tell you, but is unrestrained. So that piston is not stuck in a position. That piston can move up and down. So I'm adding heat. If I plot it on this diagram, where do I go? Up, down. The correct answer is horizontal, right? The correct answer is horizontal because we just concluded a moment ago that would be a constant pressure process, right? So, but not in this plot because I put temperature. So maybe now whoever was talking about temperature, where do we go now? That's the best answer, right? We could get a little picky. You're saying diagonally up, right? Because you're saying temperature will go up. I'm adding heat, right? You can think about doing this in the kitchen. Right? Put the water in a pan in the kitchen, turn on the stove, right? Put it on simmer so it's very slow, right? There's a difference, well, and it has to be covered, but with a lid that can move. So that's a little harder to do at home. But you get the idea. It has to heat up. And the volume will increase. So it's diagonal, but do you think it'll be steep or shallow? Steep or shallow? See, this is when the eye clicker would be good. Right? So it's going to be steep, right? Because that's liquid, right? How much will the liquid volume change if I heat it up? Not a lot. So it should be steep. So I'm going to presumably be going something like that. The temperature will increase, the volume will increase, but probably very little. It's probably going to be very hard to measure that volume change. Piston will move up a little bit. Okay, but that's not going to be happening forever. Something will happen at some point. What will happen?
It's going to turn to a gas.
Okay, but that's that because the process is in quasi-equilibrium. It's going to be very slowly. So if I am paying attention and looking at my cylinder, at some point I might see that some gas begins to appear. So maybe I see a first, a small spot somewhere turns into vapor. Now this could get complicated if you're doing it, say, in the kitchen and you're putting it on the stove. Where will the first bubbles appear? At the bottom, right? You can all see them. You put the water in the pan, put it on the stove. You see the little bubbles appearing at the bottom because that's where the heat is coming from. Right? So gravity is playing a role. The location of the heat source is playing a role. Those are realistic conditions that we're trying to avoid here. But we know that there's going to be a bubble somewhere. And then more bubbles, and more bubbles, and more bubbles. Right? So what's going to happen to the volume now? It's going to increase a lot more. So this won't be as steep anymore. Does anybody know how it will be? It'll actually be the most shallow you can think of. It's going to be horizontal. Because what's happening to the heat, so let's put a mark here that denotes when I first saw gas. Right? I first saw gas there. And now we're going to be going this way. The volume will increase. Why is the temperature not increasing? If I'm still adding heat.
Because the water's becoming gaseous.
Where is the energy going from the heat?
Change form.
To break the bonds of the liquid and turn it into vapor. So that happens at constant temperature. All right? So as I keep going here, from the first appearance of gas and more and more and more and more gas, the volume will change considerably. In fact, now it will be very noticeable that the volume is changing. And I, in fact, probably wouldn't be able to put it on the scale. If I make this plot to scale, this is going to go way to the right. But I'm not going to do that, of course. I'm going to pretend that at some point I see what situation? No more liquid. So at some point here, I'm going to put it another open circle. No more liquid. All the liquid is gone. It all turned into vapor. Now, what's going on inside the system? Again, it depends, because if there is gravity, what would happen? If there is gravity, wouldn't we see something like this? Right? If there is gravity, the liquid will sink to the bottom, will stay at the bottom, the vapor will be on top. But if there is no gravity, it isn't clear exactly where the vapor is going to be. It could be anywhere. Right? So let's not be too worried about where the vapor is. We know that as we are going from the first open circle to the second open circle, I go from a situation where everything is liquid to a situation where everything is vapor. Right? So when I reach this open circle, all I have is vapor. What happens if I keep adding heat? So now I have something like that. All I have is vapor, and I keep adding heat. What happens? Volume will increase. Temperature will increase. Is it going to be steep? Like before? Yeah, it won't be as steep as this one. It will be a lot less because the vapor can expand, right? A lot more than the liquid. Right? So it'll be something like that. And that'll be my experiment. And I end whenever I want to end. Things are getting pretty hot, so at some point we end it so that we don't burn the place down. And that's our experiment. So now I say, all right, very good. Let's repeat the experiment Let's repeat the experiment, but change the pressure. Remember I told you that we could control this pressure? So let's repeat this experiment 2 more times. Let's do 2 more experiments. One at a higher pressure than we did the original experiment, and another time at a lower pressure. We're always going to start with water. Let's say that we start at the same temperature. Start at the same temperature, but one time we're going to crank up the pressure, second time we're going to drop the pressure. So let's do, for example, the one where we crank up the pressure. Same temperature, but now I crank up the pressure. What happens to the volume? At the initial state. It's going to be smaller because I'm compressing that liquid as hard as it is. I'm compressing it a little bit. So if I start with the same temperature but at a higher pressure, you all agree with me that we're going to start perhaps somewhere over here. Again, it's going to be a very insignificant or very hard to detect variation in volume because it's liquid. I'm cranking up the pressure, but it will compress a little bit. So I'll probably start somewhere here. Now, qualitatively speaking, is the experiment going to be different? In a qualitative sense, the same thing will happen. So I'm going to still be going like that. All right? When will I see the vapor for the first time? At a higher temperature. So I'm going to see the vapor perhaps there. It will be at a higher temperature because if you boil a liquid at a higher pressure, it will take a higher temperature. That's why you have those pressure cookers. Yes?
Would the slope be the same? Like, wouldn't it be steeper than
It won't be the same, but it doesn't really matter whether it's steeper or less steep. It doesn't matter. There will be a difference there, but it's not important to us right now. It'll be steep. In fact, you can see how I made it a little less steep here because I had to get to a place that I wanted to get to. So, so that's what will happen. And if I do the experiment at the lower pressure, where do I start? Well, now it'll be a little bit to the right, because I have less pressure. Qualitatively, it will be the same, so I'll be going up. All right? But now, when will I see vapor? At a lower temperature, right? You all have gone camping, right, in the mountains? Or some of you have, right? You boil water, say in Big Bear, it'll start boiling at a lower temperature. If you're high enough, you can actually stick your finger in there. It won't be 100 degrees Celsius. It'll be a lot less. Right? So these are the 3 scenarios. The original experiment, the experiment conducted at a much higher pressure, and now the experiment at a lower pressure. And again, my open circles here denote when I first see vapor. So of course, what happens after that is the same as before. Liquid turning into vapor, and then I'll find out that at some point all the liquid is gone. It'll look like that, and at the low pressure I'll be going like that, and then at some point all the liquid will be gone. It'll look something like that. And the continuation after everything is vapor will be qualitatively similar. So when everything is vapor, then it'll go that way. And that's the end over there. And then here, everything has turned into vapor. I keep going and I stop somewhere. So that qualitatively speaking, the 3 experiments look the same. There are some quantitative differences due to the fact that we're doing the experiments at 3 different pressures. So I do all of that. And suppose now that I ask you, well, now do the experiment many more times. Right? Do the experiment so that you fill in the entire plot. What would happen if we do that? So clearly, if I do more and more lines, I'm going to just fill in the gaps in between. And suppose I tell you, well, let's join with a line all the points that denote when vapor first appeared. All right? So I'm going to do that in red. I'm going to join these points with a red line. Okay? Those are all the points where I first saw vapor. And of course, if I do it down here, I'll see even more. That's what that line is. And then I say, well, do the same thing on the other side. When you see the last drop of liquid disappear, which is the open circles here on the right-hand side, join all those with a line, and you just use red again. So I say, well, I'm going to join that, and some more over here. And the question is, what's going on up there? Right? So it looks like that, right? I'm just joining the dots of the first vapor and the last liquid. If I keep doing this at a higher and higher pressure, what will happen with those two red lines? They will eventually meet each other, as is obvious from the way I'm drawing this. So if I keep doing this, I might find that this looks like that. I will find that it looks like that. So the line that denotes the first appearance of vapor merges with the line that denotes the last particle of liquid, right? And they meet at a higher point here. And we give this point a name. What do you want to call it? What should we call this point? How about lady right there? What should we call that point at the very top? I'm sorry? Okay. Hat. Nobody knows? Does everybody know the name of this point?
Saturation?
No. Not that one. We call this point the critical point. The critical point. And then we also give these lines names. Right? We call this line here on the left-hand side, remember that's when the liquid, the vapor first appeared. We call this line saturated liquid line. Saturated liquid line. And obviously, what do we call this one on this other side? Saturated vapor line. So we have a saturated liquid line, saturated vapor line. They meet at the top of the critical point. Think about what happens if I do the experiment at a pressure that is sufficiently high that the blue dashed line goes above the critical point. Think about what happens in that scenario. Right? Do the experiment at a sufficiently high pressure, right, so that you are above the critical point. You start with liquid, you end up with vapor, but what happens in the middle? Right? Think about that, and then we'll talk some more next week.